Hey physics students, this is Mr. Resentes. I'm on page 90, and what I'm doing is called resolving vectors into components. The components that we're concerned about mostly is the x component, but the x and the y component is what we are resolving our vectors into. You had to do this for a homework sheet. Perhaps you recall with this homework sheet you have to have a conversion factor. The conversion factor I used was 100 meters equals 5 centimeters, and with that conversion you could reduce these numbers, such as 64 meters, into a manageable distance for you to measure. Once you measure it, you make triangles and find the displacement. The displacement is the x component. Add up all those x components and you have the total displacement on the bottom of the page. So let me show you how that works. First we need a vector, and in order to get a vector, we need well, let's start with the horizontal line here, and here's our vector. 47 meters per second northeast, 39 degrees. That'll be our vector, and we need to have an angle here of approximately 40 degrees. We're going up 4.7 centimeters. Here's our vector. Now here is our x component, or horizontal component, or x component. So when we say we're resolving it into components, we're resolving it into the x component and the y component. So here would be our y component. And how we would do this is we really just want that part of the vector that we see along the y and along the x. Alright? So we've just made a couple of triangles. We use our trigonometry skills in order to find this, these components. So here is the opposite side. This, as I said, is 39 degrees. This would be considered the adjacent, the hypotenuse, of course. And here's another opposite. This would be the y component, or the vertical. Right, and so what we could do is we could call this vector that we want here, we could call this vector vector x, because it's on the x. We can call it vector x because it's on the x-axis, and we could call this vector vector y because it's on the y-axis. And so those are the components of this vector that we're looking for. And so that's what's meant by resolving a vector into components. So simple enough. We use our trigonometry skills. Vx equals the cosine of the angle times the adjacent over the hypotenuse, and so the cosine 39 times 47 meters per second equals 36.5, and that's too many sig. That's too many sig figs. I think if all we have are 2 sig figs, all we have is 2 sig figs. Let's resolve this to 37. Let's reduce that just down to 2 sig figs and call it 37 meters per second. And then we could do the same thing for the vector y, but because we're projecting onto the y-axis, we will use sine instead of cosine, and this is not adjacent, is it? It's opposite. This is a different equation. This is opposite over hypotenuse, so it would be sine of 39 times 47 meters per second equals 29.6, and we should just use 2 sig figs and just call it 30 meters per second. Alright, so we just resolved and found the y and the x components of that vector. So if we use one of the examples, let's go to practice B, resolving vectors, page 92, and we go to number 1. We have a situation where there's a plane that's supposed to be a plane, and there's going to be a horizontal component, and we need this to be this plane to be a 25 degree angle. So it's 25 degrees, and what we want is we want the vertical component, or that's the vertical component, but we don't want that. We want the x component. We want Vx. We want to know what this is. We know the hypotenuse. The hypotenuse is given. That's the velocity of a car that's underneath it. Velocity equals 105 kilometers per hour. So as long as we know this is 105 kilometers per hour, that's the hypotenuse, we should be able to find this side of the triangle. Remember, these equations only work because this is a right triangle. So velocity x equals that's this, or this vector x. This is also a car, so the velocity x, and we're going kilometers per hour, is the hypotenuse times the cosine of the angle, because we use that equation, adjacent, the cosine of the angle times hypotenuse. And if you want hypotenuse, you divide those two. If you want adjacent, you multiply those two. So so it would be 105 kilometers per hour times the cosine of the angle 25, and if you put that into your calculator, one thing that you have to be very careful of, and that is make sure that your calculator is set on degrees, not radians. And in order to do that, you press mode, and then make sure that it's on degrees and not radians, because well, that frustrated me in the past, and I don't want it to frustrate you. Okay, now we want to find the second thing we want to do is find the y component. We just found the x component, so we do the exact same thing, but this time we're going to find the y component. Oops. And this is an angle that is 25 degrees, and this is 105. Let's say here's our little aeroplane, and this is the component that we're looking for here, this y component. Alright, so when we look for the y component, we're going to use sine of the angle, and this is 25 degrees, is opposite divided by the hypotenuse, and so it's 105 times the sine of 25 equals Vy. This would be Vy now, that's what we're looking for. And so Vy would equal 44 kilometers per hour. Now that's the y component. Now there's one other thing that you could use this for that you don't have to necessarily. We could use it for just any vector really. And if we have, let's say we have a situation where we've got an incline, and on this incline we've got a box, and we know from our previous unit that the acceleration due to gravity has direction and has magnitude, and so it's pointing straight down, and so we'll just call that A. A would be 9.81 meters per second squared. So, well, we could resolve this. We could have a vector that's running perpendicular here, and a vector that's running parallel with the plane here, and so we could resolve this into two more triangles, and we could solve for this vector, which is C, and we could resolve for this vector, which I'll call B. So we're resolving this vector and this vector. Well, we could do that by the velocity C equals the cosine of the angle 22 times 9.81 meters per second squared, and that's 9.09 meters per second squared for this vector. And then the vector B is sine 22. That's the angles, because this angle is 22, this angle would be 22, and this angle would be 22. 9.81 meters per second squared equals 3.67 meters per second squared. So we know this would have a acceleration of 3.6 meters per second squared, and that's the reason why we use an incline to slow gravity down, so that we can measure force. But remember that the sine of the angle is the ratio of the leg opposite of that angle to the hypotenuse, and the sine is of the angle of the ratio of the leg adjacent to the hypotenuse.